now going to do a Edman degradation video mechanism in our video. Wow. Okay, wasn't that hard to say? So as soon as you see this chemical, you start thinking about the Edman. Not that the guy's name is that important. You don't really need to tell me what the tetrapeptide is, but I'm just reminding you it's pro, glue, met, and F. Remember, the Edman targets the amino terminal residue. So that's the one. And if you're wanting to have a template of something to use for this mechanism, I got this one from a document titled Updated Mechanisms for Edman Degradation, Cyanogen Bromide Degradation, and ZCC coupling. So yeah, they're all three on the test. So this is it's a good handout. I just stole this from the handout. I'm going to use it as a guide for what to do here. And we're doing the red, blue first, and red. What's happening first with red? Let's describe it. A lone pair on the amino terminal residue attacks the carbon that's double bonded to sulfur, and the electrons go towards the more electronegative end. You would get an N minus after the red arrow, after the red. But you don't have to draw that if you combine that step with the N minus attacking, doing an acid base, and then the word intermole shows up because it's going to be ring size 4 to get from the N to the H. Intermolecular proton transfer is what that said. Let's do it. Lone pair on the nitrogen. Attacks the carbon that has the sulfur on it. Whoa, that arrow didn't start very well. Pi breaks, becomes lone pair on N. You have to acknowledge that you're doing one thing first. It could be colors, it could be numbers over arrows, however you like it. I'm flexible. Red first, blue second. That's just the way I like to roll. And after that, the nitrogen with a lone pair is going to grab the H. So 1, you got to put a lone pair on the nitrogen. 2, scribble out the H that's already there because I need to see its bond for the mechanism. Replace it with a real H, and then come with blue. Grab that H, and don't lose a point for not acknowledging that it has to be intermolecular. Don't throw that point away. What color is good? Purple. That arrow has to be done in intermolecular fashion. You can use intermole as the short form. Okay. What happens after that? Well, we got to draw our intermediate is what happens after that. What's not changing in this whole reaction? I need this. I think I need the carbonyl. Or is it this carbonyl? I think I need that carbonyl. No, I don't. I think I can just circle everything after the carbonyl here. Subject to further review, as they say. Because, I could have just looked at the product and figured that out. Look, no change. All the nitrogen changes. So that's okay. No big deal. Your circle should have ended before the nitrogen. Because the nitrogen does change. There we go. Not a great looking circle. R. So you're going to have R attached to NH. Attached to carbonyl. Attached to a carbon that goes to a nitrogen that has an H on it, part of a ring. That H is gone. Should look at my mechanism a little more closely. Moving our guide down because I need the room. The N is attached to a carbon that has a double bond to sulfur still, and a single bond to an N that now has an H, and the N has a phenyl. I think that's what we have. Yep. Phenyl, N with a new H from this bond. And there you go, everything else. What's next? Well, going down here. The nitrogen attached to the phenyl resonates into the sulfur, which makes a ring to the carbonyl, the black carbonyl up here. So the nitrogen with the phenyl, lone pair resonates towards the sulfur. Goes in between there. Sulfur attacks the carbonyl carbon. Carbonyl carbon breaks to, yeah, okay. I need to have a little more room to the right of that arrow. There we go. And that's eventually going to do what? That O minus. That's going to be an O minus. Oh, the O minus resonates back and kicks off the NH2R by protonating the N as it goes. Oh, yeah, that's what that means. We have water here. Do we have water in ours? No, we have HOET. Oh, don't let that mess you up. HOET is a good proton source, as good as water. HOET. So the blue arrows are as follows. The blue arrows are as follows. Lone pair on the oxygen. Need a lone pair on the oxygen. Need it to come back down. Kick off the leaving group, but the leaving group has to protonate because it's not a great leaving group. There you go. Yeah. And you're going to get this ring. You got to draw this ring. So what we have here, we have phenyl comes to nitrogen with an H and a double bond to a carbon that has a sulfur on the top, goes to a carbon eel, goes to an C, that goes to an N attached there. And the N, whoa, and the N is part of a ring. Right there. I got that right? Hope so. And a plus. And this N doesn't look so good. Now it looks good. Okay. Now it's hydrolysis time. Looks like we made OET minus. That is a nucleophile we can use instead of hydroxide in the example. It's going to do the same thing hydroxide did. Yeah. Yeah, it's going to come on and come off later. Okay. OET attacks, pi breaks. Resonate back all the way to the back to the nitrogen that has the plus charge. Okay. First step. O attacks carbonyl. Electrons back, resonating all the way through the sulfur. Through the sulfur to get nitrogen its lone pair back. And I don't know what happened there. We're going to be at this stage right here. So let's just follow our own arrows and draw what we get. Got a phenyl attached to an N with an H. And we get a single bond and a double bond to sulfur. Single bond to N. Still got that ring. And now we have off that ring, it's OET, not OH. Similar idea though. And now your phenyl nitrogen is going to be a nucleophile to do an amidation of this ester. And make an amide is what I was trying to say. Nitrogen attacks the carbonyl of a carboxylic here, carbonyl of an ester here. 2 steps, boot off the leaving group, and we're almost done. In fact, we can be done. We can be done. We can do this. Nitrogen lone pair attacks the carbonyl. Lone pair comes off, back. Purple comes back. Kicks off the leaving group, which is ETO minus. What's ETO minus going to do after that? It's going to grab the H from the ammonium right here. As long as it's a new color, you can do it right here. Oh, I love it. Purple's not the same as light blue. And we got past drawing this intermediate here, didn't we? It's just an acid base. So big picture here. And sadly, you won't have the template on your exam. That's just how we study. So you got to get to the point where we're past using the template. And that's a pretty good mechanism. 12 points. I think we'll come back with the cyanogen bromide mechanism after this. So you can copy out the first tetrapeptide to get started on your next page. On your next video, we're going to start with the same molecule, okay? This one. And I'll make it big so you can copy it. And I'm going to stop the video right now.